All right. Uh, Finished talking about vectors last time. We're going to get into particle statics today. Uh, Before I start, does anyone have any homework questions or general questions? All right, so statics of particles. When you took physics 1, you started with particles and then towards the end moved into rigid bodies. We're going to spend very little time with particles, but we're following the same sort of order sequence. So what's a particle? What? Okay, yeah. So a particle has no length dimensions of any kind. So you treat it like something the size of a point moving around. Um, no length dimensions. Does it have mass? Yes. Uh, that's actually not going to come up in statics, but yeah, particles, they don't have any length, but they do have mass. And because there are no length dimensions, everything happens at a single point. Everything's concentrated at a single point. And so you can't make any distinction between like a left side and a right side, a top and a bottom. And so because of the fact that there's no length dimensions, we lose all ability to monitor orientation. Okay? So no length means no orientation. All we can do is track the location of this thing as it moves around. And no orientation means we're not going to, with particles, the moment equation doesn't mean anything. So no orientation means no, the thing I call Rn2L, I think I mentioned that before, rotational Newton's second law, the one that says the net moment is equal to the moment of inertia times alpha. That doesn't come into particle stuff at all. In particle physics, then, the only equation of motion is Newton's second law, and that says you're already here. So F net is equal to the mass times the acceleration of the center of mass. And with particles, everything happens at a single point. So there's no distinction between the center of mass and anything else. This equation gives two equations in 2D, like the x and y components of this equation, and three equations in 3D. In statics, Newton's second law reduces to F net is equal to the zero vector. But again, that's two equations in 2D. Mostly we'll be doing two-dimensional problems, but some 3D. Two equations in 2D, three equations in 3D. And the reason it reduces to this is because in statics, everything's in static equilibrium. That's right. There's no acceleration, so the right side goes away. You can treat any object as a particle if, not is, if you don't care about its orientation. You do need to make sure that the point you use, though, as representing the object's location is the object's center of mass. If you don't do that, everything goes out of whack. So you have to treat the object's location as the object's, true center of mass. So you can do particle physics with things of any size, any dimensions. Doesn't matter, as long as you don't care about the orientation, you can use this approach. You just have to track the center of mass of the object. Like, for example, in planetary motion and astronomy, often you're treating planets and stars and whatever as particles. Obviously, those are huge things, but the calculations would be totally out of whack if you weren't representing their location using the center of mass. You'd see, if you're tracking like a single point on the outer surface of a planet as it spins around, it would be doing like a curly Q thing, and that wouldn't make any sense with the physics. It has to be the center of mass. So with particle statics, we're going to be using Newton's second law. And anytime you use Newton's second law, and let me also say, so with particle statics, we're not going to use the rotational equation. This is also true of rotational equation. So, center of mass. And Newton's second, N2L is Newton's second law, and Rn2L is rotational Newton's second law. I've sort of drifted into a lot of abbreviations over the years, and then I forget what classes I've mentioned what those stand for, But anytime you use Newton's second law or rotational version of Newton's second law for the rest of your life, you need to draw an associated free body diagram. There's another one. Free body diagram. Free body diagram. I'll abbreviate that FBD. And you might think like, okay, well, if I if I die and I'm brought back, you know, then, my life sort of ended. So maybe I don't have to draw free body diagrams, after that. But no, you have to draw free body diagrams. Anytime you're alive, you have to draw free body diagrams. And so these are the rules for free body diagrams, for the steps to follow. So the first one is you have to choose a body to isolate. It has to be some enclosed chunk of material. Um, it can be an actual whole object, or it can be a part of an object, or it can be a collection of objects. The only rule is you have to be able to draw an imaginary boundary around it that closes everywhere. Okay, there has to be a clear boundary between what you're calling your chosen object and the surroundings. And second, draw a closed outline of the of that chosen body. With no external objects and no internal details. Okay, so like for example, say that there's a car sitting on the grass. And there's a pig on the hood of the car. I don't really know if pigs' joints are like that. Yeah, that's the thing that identifies it as a pig. And there's a, like a helicopter trying to pull the pig off this car, maybe. It's way off in the distance. That's why it looks so little. Okay, so there's a lot of stuff going on in this picture. That's the point of all this. And so a free body diagram of the car looks like this. Okay. Okay, so this is the way it should look. It should not look like any of these. So first, what about like a stick figure of the car, that doesn't work because it's not a closed outline. The whole point of the free body diagram is, well, there are a couple points, but the whole point of the way that you draw the object itself is you're trying to be very clear and succinct to yourself and whoever's looking at it about what's inside your chosen body and what's outside. Okay, so if you don't draw that outline, like from that picture, you can't tell, are you isolating some part of the, undercarriage of the car, or are you also including, you know what I mean? It's not totally clear what's in and what's out. That boundary is what tells you what's in and what's out. Yep.
How specific do you need to get? Just draw your free body diagram as like that rectangle for a car?
Yeah. The more, I think the answer is the more, if your chosen body is just an object like a car, then yeah, it probably doesn't make too much sense to worry too much about the details. But there would be problems where you'd be isolating, okay, I want to isolate the wheels and the metal connected to the bottom of the car and a little bit of metal going up the back or something. There'd be reasons to do stuff like that. And the more you're picking out pieces of a whole object, I think the more careful you need to be about that. Because the answer is just, you want to be careful enough to be very clear to yourself and whoever looks at it, what's in and what's out, some other things not to do. What about, okay, so we're isolating the car. There's the car. Don't do this because that grass is an external object. We don't want to be confusing about whether that the grass is included and we're concerned about forces acting on the grass, or whether only the car is included and we're worried only about forces acting on the car. And then the last one. So there's the car. And there's the pig. Okay. Don't do that because we're not isolating the pig. And so no external objects should be included. Right? So that was step 2. And then the third step is draw all of the loads acting on the body. Loads, let me be more specific about that. So when I say loads, I'm talking about both forces and couples. Talk about couples pretty soon, not today. Acting on the chosen object. Applied by the surroundings. Okay, so all we're concerned about are the external loads. And that's amazing news because if we had to always, in our free body diagram, if we had to include all of the forces applied by one part of what's inside this boundary to another part of the inside of this boundary, we'd be here forever on the first problem we did, talking about like atomic forces and whatever, But we get to leave out anything that's happening inside that boundary. If the wheel, so like the wheel's applying a force to the car is applying a force to the wheel, we don't have to put that in the free body diagram. That's great news. And this can be a little bit confusing as problems get more complicated. And one thing that I think it's helpful to remind yourself is that there are only two kinds of forces that are going to come up. There's only two ways this can happen. The first is field forces. And in this class, I can even simplify that more. That only includes weight. It also could include electric fields, magnetic fields, but for us, we're just talking about the object's weight. And then the second way is places along the boundary, along the object boundary, where the object contacts the outside world. Okay, so let's look back at this thing. So there's a lot going on in that picture. How do you know once you've dealt with all the forces on the car? Well, if you're sort of systematic about it and you say, okay, well, first I got to apply the weight, and you deal with the weight of the car, and then you just go around the boundary mentally looking for places where the outside world touches it. Once you've gone all the way around the boundary, you know you're done. So I'll start back here, go around. Here's contact. That back wheel contacts the ground. Here's contact. The ground contacts the wheel again. Go around. Here's contact with hoof. Another contact with the hoof. There's no other contact. So all we have to deal with is this, 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 and this. And if we're treating this car as a particle, we can just, since everything happens at a single point, we can, let's say the ground only touches it at one, concentrates into 1 point. The hoofs only concentrate into one. So we have a force on the car from the ground and a force on the car from the pig. And then, what about the rope and the helicopter and stuff? Those definitely affect the forces that the pig applies to the car, but those aren't touching the boundary of our chosen object, so they don't appear in the free body diagram. Okay. So weight force, boundary, then you know you're done. Mathematically, forces fall into two categories. Forces with unknown directions and forces with known directions. So let's do known first. So if you know the direction of a force, draw an arrow in the known direction. And associate that arrow with a scalar variable or value. So for example, if you have a mass that's connected, let's say this has a mass of 10 kilograms, and it's connected to a cable that attaches to the wall over there and another cable that attaches to the wall over here. Then the free body diagram. There's the mass. We know that weight applies a downward force with a magnitude of 10 times 9.81, so 98.1 newtons. And then those cables apply forces parallel to the cable away from the chosen body. Sometimes when these get complicated, this isn't a real complicated one, but with pulleys everywhere and whatever, I think it can sort of clarify things to you if you imagine including just a tiny little bit of the cable in your chosen body. Okay, so now what we're choosing is these sort of infinitesimal chunks of the cable in addition to the body. And then the force that's applied by that cable to the body just acts straight out of the stump. So you can write this as, let's call this one P1, P2. And we dealt with the forces that way because we knew the directions of those forces. Whenever you have forces with known directions, you're going to be dealing with unit vectors in some way or another. So notice, anytime a force has a known direction, it will be represented mathematically as a scalar times a unit vector. And that unit vector is in the direction of the arrow. So with these cables, you have to figure out a unit vector pointing that direction. And then the total force vector is T2 times that unit vector. Okay. With this one, the unit vector is that direction. The total force is T1 times that unit vector. What about this one? Because when you think of the weight at first, it doesn't really seem like you need a unit vector for that. That's just 98.1 in the negative y direction, 0, negative 98.1. And yeah, like you're familiar enough with that you're not going to really think about it as a unit vector. But really, if you think about this arrow as being represented by the unit vector 0, negative 1, okay, That's the unit vector in the direction of that arrow. And then you multiply it by 98.1. You're still taking the magnitude of that vector and multiplying it by a unit vector representing the direction. Okay. So that is if we have forces with known directions. If we have forces with unknown directions, then draw small coordinate axes. Well, they're not really, I shouldn't say that. Draw small vectors in the directions of the coordinate axes. And associate that with a vector variable or value. So if we go back to the car, pig, helicopter example. In a free body diagram of the car, well, the car has weight, so I'll write that as mg. And now, what do we know about the directions of the forces applied at the contact? Well, we can make some assumptions, but for now, let's say we don't know the direction of the force applied to the wheels by the ground. We don't know the direction of the forces applied to the hood by the pig. So I'm just going to write this as, so there's the two vectors in the coordinate directions. I'll write this as F1, F2, F3, and F4. So those are the two hooves. Those are the contact with the grass. And just because you draw a correct free body diagram, it doesn't mean that you can necessarily solve for all the things you want to. And this is an example. From Newton's second law, this is a 2D problem, right? So how many equations do we get from Newton's second law? Two equations. So how many variables can we solve for? Two. You can only solve for one variable with each equation. And what we have here is every unknown vector has two variables associated with it, an x and a y component. So here we have 2, 4, 6, 8 variables we want to solve for. We only have two equations. So unless we can come up with some other things that are known about this problem, we're sort of stuck at this point. Usually we will be able to find other things, but all right, any questions about that? So that's it for free body diagrams. if you do your free body diagrams carefully, it gives you everything you need for the left side of Newton's second law. So remember, so Newton's second law says add up all the forces, that's equal to the mass times the acceleration of the center of mass. Or for us in statics, add up all the forces, that's the left side, and it's equal to 0. Okay, straight from the free body diagram, we're given all these forces. So when you go to Newton's second law, you just have F1 plus F2 plus F3 plus F4 plus the vector representing this is equal to 0. Okay, and in statics, all there is a left side of Newton's second law. You just set it equal to 0. In dynamics, the right side often is the trickiest part to deal with, but all of this stuff we're doing here is still going to apply in dynamics. The idea of the free body diagram in dynamics too is to give you everything you need to know about one side of Newton's second law. Okay, okay, that's it for now.
Is that usually the force?
That's always that's what I mean. Yes, the force side. All right, let's do a couple examples and see how this fits into the second law. So let's say that there's a mass connected to a pulley, and there's also a pulley connected to the ceiling. And this object is supported by a cable that goes from the ceiling over that pulley connected to the mass, and then up to the pulley connected to the ceiling, and then downward force T. And let's say the mass of this object is 100 kilograms. What's the force T required to hold up this mass? Well, this is sort of a cool fact about pulleys. The pulley itself, all it does is change the direction of that cable force. But if you set up a system like this, you can get, use pulley advantage. And we're going to see that this tension here that's required to hold this up is half of the weight of the box. Okay, that's something they use that's taken advantage of in a lot of different industries. So let's draw a free body diagram of the mass. And I'm going to include that hanging pulley, the connected pulley. All right, so what forces are acting? Well, weight, and the weight is 100 kilograms times 9.81, so 981 newtons. And now we're going to go around the boundary of the object, looking for contact between the boundary and the outside world. Okay. So there's nothing all the way around here. But when you get up to there, a cable that's not part of what we're, that's not part of our chosen body touches there, right? So there has to be a force. And then when you get over here, same thing on the other side. That cable's touching the boundary over there. So I'm going to do that thing where I include just an infinitesimal section of the cable at both of those two contact points. And now the cable force acts directly out of that, little stump. Since this is all one cable, it applies the same force everywhere. So, yep.
How come you wouldn't draw that force from basically the center of the pulley, considering it's...
Yeah, that's okay. That's a good question. So, yeah, I guess I sort of glossed over that. So, what we're really including is we're not skipping the whole cable. Our chosen body is the mass and the pulley and all of the cable that goes underneath. Okay, so that's all part of our chosen body. And so what really happens here at this contact is we're talking about the place where the part of the cable that we've chosen contacts the part of the pulley that we haven't. Any other questions about this? Okay, so Newton's second law says this 981 is in the negative y direction, so that's 0, negative 981. Each of these is in the positive y direction, so that's 0t plus 0t. And all that's equal to 0. We're assuming that this isn't accelerating. So we get two equations. The first one says 0 equals 0, so that doesn't help. But the second one says negative 981 plus 2t is equal to 0. And so t is equal to 490.5 newtons. So to hold up that thing that has a weight of 981 newtons, you only have to apply a force to the cable of 490.5 newtons. That's pulley advantage. Okay, let's do one more with a pulley. So let's say there's a pulley like this, and the cable is supporting a 100 kilogram mass. And the cable goes over the pulley and then connects to the wall. So first, let's figure out the tension in the cable. And then second, let's figure out what's the force vector the cable applies to the wall. So a free body diagram of the mass. There's a downward force equal to the weight, so 981 newtons down. And then the only other place the outside world contacts the boundary is where that cable connects. And so there's a force like that that's equal to T. And we're trying to find that value T. So Newton's second law says 0, negative 981, plus 0T is equal to zeros. The x equation says 0 equals 0, so that's useless again. But the y equation says negative 981 plus t is equal to 0, so t is equal to 981 newtons. So that's the cable tension. And all along that cable, that's the value of the tension. Any questions about that first step? And then second, we want to figure out the force vector that cable applies to the wall. So think about the direction of force that the cable applies to the wall. You can think about the wall with a little infinitesimal chunk of the cable attached to it. So that force vector is this way. You know, this is the wall. And this force vector is equal to T. All of the forces applied by that cable are T, which is 981 newtons. And so the force vector is, you can think of that as 981 newtons times a unit vector in the direction of that arrow, which is 1, 0, or 981, 0 newtons. Any questions about that? When we're talking about vector variables, force vectors, there's a naming convention that we're going to use. So this is the convention for naming force vectors. And you don't want to use this convention when you're talking about the scalars that represent a force with a known direction. So don't use this for scalar force variables. Force vectors, and it works for couples too when that comes up. So don't use this for scalar variables. In the conventions, it's F with two subscripts. So let's say FAB. And what this means is FAB is the force vector applied to body A by body B. This is the order that I'm going to talk about in this class. This is a nuisance, but this isn't universally done. It's done half the time or something. It tends to be the case that engineers use this convention and physicists use the other convention that says where FAB would be the force applied by A to B, like backward convention. So there's nothing I can do about that, but this is the one I'm going to use in this class. Okay. If any of you are taking Physics 2 with Tony Weinbeck right now, anybody? No? Okay, I don't know what he does, but I know that Tony uses the convention, the opposite convention to this, and pain in the butt, but there's nothing I can do about it. Let me show an example using this. So let's say we have two boxes resting on the floor on top of each other like this. Say the top one is 20 kilograms and the bottom one is 50 kilograms. And let's say there's a downward force of 100 newtons applied to the top one. And horizontal force also applied to the top one of 50 newtons. And there's a friction contact between the two boxes and a friction contact between the bottom box and the ground. Friction contact between two objects produces a contact force with an unknown direction. We want to figure out what's the force applied to the 20 kilogram box by the 50 kilogram box. So we're trying to figure out the force. What are the subscripts here? If we're going to call the boxes 20 and 50, what's the first subscript? The 20, yep. So the first subscript is the one that the force is applied to, and the second subscript is is the object that's applying the force. So this is the force vector on 20 by 50, comma, just to make it clear, it's not all one number. So I'll draw a free body diagram of the 20 kilogram box. There's a weight force of 20 times 9.81, so 196.2 newtons down. And now we're going around the boundary looking for contact. We know that we don't know what kind of contact it is, but we know there's something contacting the boundary producing that 100 Newton force. And then there's also something on this boundary producing the 50 Newton force. And the last place that the outside world contacts the boundary is the contact between those two boxes. That's a friction contact, so we don't know the direction. And this is the force acting on the 20 by the 50. So Newton's second law says 50, 0 plus 0, negative 100 plus 0, negative 196.2 plus F 2050 X component, F 2050 Y component is equal to zeros. The X component of this equation says 50 plus F 2050 X equal to 0. So F 2050 X is equal to negative 50. And the Y equation says negative 100 minus 196.2 plus F 2050 Y is equal to 0. And that says that F 2050 Y is equal to positive 296.2 newtons. Oops. And so if you put those together, it tells you that the force vector 2050 is equal to negative 50, positive 296.2 newtons. Yep.
Is it going to be normal in here to not break the normal force apart from static friction?
So yeah, that's sort of a yeah. In physics 1, you didn't do it that way. In this class, for friction contact, it is going to be normal. It is going to be usual to do it this way because we don't. There's no benefit to us in these problems of breaking that vector up into a normal force and a friction force. We're talking about, in this class, we're only talking about static friction. And when you do static friction problems, remember when you're using the coefficient of friction, all you can do using that coefficient of friction is figure out the maximum force that the static friction can apply. Well, we're not generally going to be at the maximum. They're just going to be somewhere underneath the maximum value. And so that coefficient of friction won't do us any good, you know. And so, yeah, we're going to do it like this. So what we have here is, if you wanted to break it up into a normal force and a friction force, the normal force is the force in the positive y direction in this problem, and the friction force is that negative 50 in the x direction. But we might as well just do it as vector components and leave it at that. You can imagine if that box, instead of sitting on a flat surface, was on a nuclei like this, okay, we go through all this moderately painful stuff to break up the force vector, this force vector, into a normal that's that way and a friction that's that way. And we might as well just leave it as a vector. This is all that matters to us, is knowing, you know. The reason it doesn't matter is because of that thing that I said before, that the coefficient of friction doesn't help us. And so we might as well just leave it in that vector form. Any other questions about that one? Okay. The reason that I gave you that sort of ugly, wacky sign convention is for Newton's third law. So let's talk about Newton's third law. And I'll abbreviate that N3L. Newton's third law is the one that says for every action there's an equal and opposite reaction. That's not a very, like, mathematically, that's not a very helpful way to describe it. So for us, we're going to think of it as meaning two things. So we'll treat differently depending on whether a contact force has a known direction or an unknown direction. So a contact force between two bodies has a known or unknown direction. In the case of a force with an unknown direction, it's especially easy. So if you have a contact force between body A and B with an unknown direction, then Newton's third law says FAB is equal to negative FBA. So the force on body A by body B is just the negative of the force on body B by body A. With a known direction, if you're dealing with the contact force between A and B, then the force on one body is, some known direction with some variable value. The force on the other body is the exact opposite vector. Let me try to draw that more carefully. With the same magnitude, same variable value. So when you're switching bodies, switch the arrow to the opposite direction and keep the label the same. Okay, so let's go back to the two boxes sitting on top of each other. Where we had the 20 kilogram box sitting on the 50 kilogram box. And there was a 100 Newton force acting down on the 20 and a 50 Newton force acting to the right on the 20. And we want to use the result that we got previously to find the force applied to the 50 by the ground. Well, the result that we got before was that the force on the 20 by the 50 was equal to negative 50, positive 296.2. So now let's do a free body diagram of the 50 kilogram box. And what do we know about the forces acting on this? Well, there's a weight of 50 times 9.81, so 490.5. And now going around the boundary, there's contact at the ground. With that double subscript notation, what would we call this? The force on, call that the 50, produced by the ground. And now just keep going around. At the top, we have contact, a force applied to the 50 by the 20. So I'm going to write that as force on the 50 by the 20. Nothing else making contact with the boundary. So what about that 50 Newton force and the 100 Newton force? Should those be in here? Yeah, they were in the 20 in the other one. So yeah, they're not touching this boundary. And so they should not be in this free body diagram, and they won't come into this problem. They will affect, their presence there does change what all the forces are, but it'll come out this way. Those should not come into this free body diagram because we went around the boundary and they weren't there. Okay. So now this F5020 by Newton's third law is equal to negative F2050. And negative F2050 is equal to positive 50, negative 296.2. So Newton's second law says 50, negative 296.2 plus 0, negative 490.5 plus the thing we're trying to find, F50G X and Y components is equal to zeros. And so the X component of this equation says 50 plus F50GX is equal to 0. Y component says negative 296.2 minus 490.5 plus F50GY is equal to 0. And so solve for those two components. And you get the force on the 50 by the ground is equal to an X component of negative 50 and a Y component of 68.86. 688.6. 686.7. Is that what you said? 786.7. Okay. 786.7 newtons. Okay. So that's using Newton's third law with force vectors whose direction you didn't know, representing them as vectors. Let me do a quick example with ones where you do know the direction. Okay, so let's say that there's a floor and a wall, and there's a 50 kilogram box against the wall, and then a 30 kilogram box next to it. And there's a 100 Newton force applied to the 30 kilogram box. Let's say that this contact is frictionless. Just need to draw three body diagrams of each box. So a free body diagram of the 30 kilogram box. There's a weight force. 30 times 9.81 is 294.3. A frictionless contact is just a normal force, so I'll call that N30. The contact force between the 30 and the 50 they're pushing on each other, so both of those two forces are toward the chosen body. I'll write that like that. And then the only other force is the, what did I say that was? 100. Any questions about that one? That R is so you can think of it this way. The combination of that R and the arrow is the force vector on the 30 by the 50. It's just that in this case, we know the direction of the force. They're pushing against each other. It stands for reaction, but it's arbitrary. It's just a variable, yeah. And now the free body diagram of the 50. There's the weight of 50 times 9.81. There's the normal force. We'll call that N50. There's the force that the wall applies to the box. You can think of this as the force vector on the 50 by the wall. And then the Newton's third law part says that we're dealing with a contact force between the 30 and the 50. If the force on the 30 is R pointing to the left, then the force on the 50 has to be R pointing to the right. So I'll draw it like this. You can see that if you treat this force with a known direction combined with the unit vector of its direction, it ends up telling you the same thing that Newton's third law tells you with that double subscript. This force vector is equal and opposite to this force vector. So we do it by just changing the direction of that arrow. Any questions about that? Okay, well, I'll give you some problems to work on with this stuff. And on Thursday, if you have trouble with any of the problems, I'd be happy to spend some time doing examples. Okay, that's all.